Let's elucidate quantum cryptanalysis. In this video, we're going to explore the quantum algorithm for order finding. We will investigate the quantum state that must be prepared prior to measurement. Let's consider two registers of qubits. The control register consists of alpha qubits. The target register consists of beta qubits. We're going to write down a quantum state that must be prepared prior to measurement. And then we're going to do some manipulation and re-express that quantum state. So first, let's consider the control register, which consists of alpha qubits. We need to prepare a uniform superposition of all of the alpha qubit computational basis states. We can write that as the normalization coefficient, 2 to the power of minus alpha on 2, then the sum over the index z, which goes over all of the elements of the integers mod 2 to the alpha. And then we're going to have the states. The states are going to be labeled by z, and we're going to put a superscript up here, and this superscript alpha tells us that it takes alpha qubits to represent this state. So Z is a label for an alpha qubit computational basis state. And we're summing over all of the possible values of Z. And that's why we need this normalization coefficient over here. So in total, there are 2 to the power of alpha qubit computational basis states. 2 to the power of alpha is the dimension of the Hilbert space. So we could also write this as Z going from 0 up to 1 less than 2 to the power of alpha. And we can equivalently write this in binary. So these values of Z can be written in binary notation. For example, when Z is equal to 0, that corresponds to a string of alpha zeros. So we could write that over here. And then we could also consider another value, which is 1 less than 2 to the power of alpha. In binary notation, that would be a string of alpha 1s. And then we can consider all of the other intermediate values. So in total, there are 2 to the power of alpha. We can create this uniform superposition of all of the alpha qubit computational basis states by first initializing in all zeros and then applying Hadamard gates to all of the alpha qubits in this control register. So that will produce this state. Now let's have a look at what's happening with the other register, that is the target register. The target register needs to be prepared in a state that is labeled by f1 of z. So z is the label for this function. And f1 we previously defined when we were talking about hidden subgroup problems. So f1 of z is the same as a to the power of z mod n. So we're doing modular arithmetic. We're working mod n. And this register contains beta qubits, so I'm going to put a little superscript beta. So this is a beta qubit state. And we can also express it in binary. So when we do a to the power of z, we're doing that mod n. And a is chosen such that it is between 1 and n, and it is co-prime with n. So the goal of this algorithm is to find the order of a mod n. So we're using the notation where that is equal to r. We want to find that value of r. And this is almost the state that we need to prepare before measurement. But once we've prepared this state, we need to apply the inverse quantum Fourier transform to the control register. And we can denote that by f sub 2 to the alpha dagger. This dagger tells us that we're applying the inverse quantum Fourier transform. And this subscript over here of 2 to the power of alpha, that specifies the dimension of the Hilbert space. So now this is the state that we're going to prepare prior to measurement. And now we're going to manipulate this state and get it in a format where we can see the value that we want to measure. And we can actually quantify the probability of measuring that desirable outcome. So before we do that, we need to introduce some eigenstates of a unitary operator. So previously we dealt with a unitary operator, u sub a. When this unitary operator acts on a beta qubit state, it has the effect of multiplication by a. And this function is a to the power of z. So it has the effect of changing this input z to z plus 1. That's what this unitary operator does to a state like this. But we can also introduce some different states, which are eigenstates of this unitary operator. And we're going to label these eigenstates as lambda specified by zeta. So here we have zeta. And this is a beta qubit eigenstate of this unitary operator. The eigenvalue has the form e to the 2 pi I zeta divided by r. And I'll just write that as r to the power of minus 1. So this is the same as the ratio of zeta and r. So zeta divided by r. And then we can write the eigenstate again. And the eigenstate is specified by this value zeta. And we're going to use these eigenstates to express this state over here. So now let's do some algebraic manipulation. We're going to expand this term and we're going to expand this term. So we need to write this normalization coefficient of 2 to the minus alpha on 2. And then we have the sum over the index z ranging over all of the values from the integers mod 2 to the alpha. And then we're going to have a similar expression over here, but we're going to have some complex exponential factors. So again, we have a normalization coefficient of 2 to the minus alpha on 2. Then we have the sum over an index which we will call x, and x also ranges over the integers mod 2 to the alpha. And then we're going to have e to the minus, this minus is because we're dealing with an inverse quantum Fourier transform, 2 pi I, and then we're going to have z x times 2 to the minus alpha. So 2 to the alpha is the dimension of the Hilbert space, and here we're dividing by 2 to the alpha, and that is written with this minus sign over here. So these are the complex exponential factors, and then we have to change the label from z to x. So we have x, and this is an alpha qubit state. So that is just this inverse quantum Fourier transform being applied to these alpha qubit computational basis states labeled by z. So now we've changed the label to x. And let's also have a look at what's going on over here in the target register. So this is the control register. Now let's have a look at the target register, which consists of beta qubits. We can write this as r to the power of minus 1/2 times the sum over an index, which we will call zeta. That's the same zeta over here. And zeta ranges over the integers mod r. So in other words, zeta goes from 0 up to r minus 1. So it's just like for these indices, they go from 0 up to 1 less than 2 to the power of alpha, which is the dimension of the Hilbert space. Over here, we're going from 0 up to 1 less than r. So those are the possible options. Here we have r options in total, and that explains this normalization coefficient of r to the power of minus 1/2. And we can write this as e to the 2 pi I, and note that now we have a plus, so it's the opposite sign to over here, and that is by convention. So we have this sign convention over here. We're defining the inverse quantum Fourier transform as having this minus sign present here. You could also define a separate convention, and then you wouldn't need to write this dagger in this location. So here we have e to the 2 pi I, and then we have z zeta divided by r, and I'll write that as r to the minus 1. And then we have the eigenstates lambda zeta. So the eigenstates are specified by this parameter zeta. And zeta and z are together in these coefficients over here. So whatever input z we have in this function f of 1, that input is going to appear in these complex exponential factors. So that's where that input gets mapped to. So we're rewriting this state over here as a superposition of eigenstates of this unitary operator, which has the effect of multiplying by a. So that's what we've done over here. We've rewritten this, we've expanded the quantum Fourier transform with this inverse convention, and we've also expanded this as a superposition of eigenstates. Now let's do some manipulation. So we'll move some of these sums around. we can write this as r to the minus 1/2 times the sum over the index zeta ranging over the integers mod r. And then we will write this sum over here. So we have the sum over x ranging over all of the integers mod 2 to the power of alpha. And now I'll change colors because we're going to group a term over here. I'm going to identify that as a coefficient. We're going to combine these two coefficients, and that's going to turn into 2 to the power of minus alpha. So because we have 2 to the minus alpha on 2, we have 2 copies of that. That's the same as squaring it. That gives us 2 to the minus alpha. And then we're going to have the sum over z. So sum over z ranging over all of the integers mod 2 to the alpha. So that's 0 up to 1 less than 2 to the alpha. And then we're going to have these complex exponential factors, which we will merge. We'll merge these complex exponential factors together, and we're going to factor out z, and we're going to treat z as an exponent. So we have e to the 2 pi I. Then we're going to take this pair over here, zeta divided by r, and we're going to subtract this minus sign over here, subtract x, but I'm going to shift x. I'm going to shift x by the alpha bit approximation of zeta divided by r. I'm denoting that alpha bit approximation with these square brackets. Now close this bracket, multiply by 2 to the minus alpha, because we have to multiply by 2 to the minus alpha so we can add these terms together. And I'll close this bracket over here, and another bracket, and then this is all being raised to the power of z. So using exponential laws, you can bring this z inside, and then you would have z zeta divided by r. That's this term over here. And if you undo this shift, you will have z times this minus x times 2 to the minus alpha. So you can see that I've just combined these complex exponential factors into one big complex exponential factor, and this z is now playing the role of an exponent. And now we'll go back to black. We need to change the label from x, because we've just shifted x. We have to change that label to x plus the alpha bit approximation of zeta divided by r. And this is an alpha qubit state. And when you see this addition inside of this ket, this is actually addition mod 2 to the alpha. So we have to do some modular arithmetic over here. And that's because we only have 2 to the alpha options. So we take all those values of x, and then we add this alpha bit string. So we add those guys, and this is addition mod 2 to the alpha. And we can't forget these eigenstates. We have lambda specified by zeta, and this is a beta qubit state. So this is the state of the control register, and this is the state of the target register. The control register has alpha qubits, the target register has beta qubits. And then we have all these sums over these coefficients. So you can see that I've written this in a separate color because I'm going to identify this as a coefficient. And now we can rewrite this whole expression. We can write this as the sum over, so first we need this normalization coefficient, then the sum over zeta ranging over the integers mod r. And we're still going to need this sum over x, which is going to range over the integers mod 2 to the alpha. And then we're going to rewrite this as a coefficient c, which is specified by zeta and x. So you can see that x and zeta are going to specify this coefficient. And now that we have this coefficient specified, we can write the rest of this expression. We have x plus this alpha bit approximation zeta divided by r, and we're doing addition mod 2 to the alpha, and then finally we have this eigenstate specified by zeta. Now let's unpack these coefficients, because these coefficients are going to allow us to quantify the probability of measuring outcomes. And we want to measure this alpha bit approximation of the ratio of zeta and r, because we're going to be able to extract the value of r from that. Now let's rewrite this coefficient over here. So we have c, which is specified by zeta and x. Because we can identify this as a geometric series, we're taking the sum of a geometric series. And we can write this in a far more condensed form. Another thing we can do is all of this stuff in the brackets here, we're going to relabel that. So all of this, we're going to relabel that as c. So the Greek letter xi is going to represent all of this stuff in the brackets here. And then we can use the fact that this is the sum of a geometric series, and we can write this as 2 to the minus alpha, that's that normalization coefficient, and then we can write this as 1 minus e to the 2 pi I c times 2 to the power of alpha. That's the number of terms that we have in this sum, 2 to the power of alpha, and then we're dividing this by 1 minus e to the 2 pi I c. And this is without the 2 to the power of alpha. So this comes from the formula of the sum of a geometric series. But this is not going to give us the probability. We have to take the square of the absolute value of these coefficients, and that's going to give us the probability of measuring states. So let's write that over here. So the absolute value squared of these coefficients, which are specified by zeta and x, that can be written as 2 to the minus 2 alpha. Now, because we're squaring this, we have to add a factor of 2 up here. And then we're going to take the absolute value squared of the top and the bottom of this quotient. And there's going to be some factors which cancel, and we're just going to be left with the absolute value of sine of pi c 2 to the alpha all squared divided by the absolute value of sine of pi c all squared. So we have the absolute value squared of these values, and when you convert from this to this form over here, when you take the absolute value squared, you're going to get another factor, and that factor is going to be the same in both the top and the bottom, and that factor is going to cancel. So we're just left with this. And now if you substitute this term over here, this xi, for all of these values, you're actually going to get the equation which specifies the probability for all of these zeta and x values. So now let's consider the special case where x is equal to 0. What we want is to choose the parameter alpha such that we get a peak close to x equals 0. So the approximation that we're looking for has the following form. We want to get x equal to 0, so then we get all of these other terms, they disappear. This coefficient is only going to be close to 1 for that term. So that means we're just going to have the sum, first we need the normalization coefficient, times the sum over zeta, ranging over all the integers mod r. And then we're going to have these states over here, and this x is going to disappear in this approximation. So I'll write this as approximately equal to, so this is not quite equal to, this is just an approximation. And then we'll have the alpha bit approximation of zeta divided by r, and then the eigenstate specified by zeta. That's a beta qubit state. Now, we're not really interested in the result of measuring this target register. We're only interested in the result of measuring this control register, which consists of alpha qubits. So when we perform that measurement, we're going to get an alpha bit string. And that alpha bit string is going to give us a decent approximation of zeta divided by r. So we actually have an integer multiple of the reciprocal of r. R is the order. So we're going to have to do a bit more work on a classical computer to extract this information. And you can see that in this approximation, we've gotten rid of this x, and we're just measuring this alpha bit approximation of zeta divided by r. But if this approximation is a valid approximation, we're going to get the desired outcome. But what happens if it's not a valid approximation? Well, then we have to choose a different parameter alpha. We need to change the size of this control register of qubits. So we can add more qubits, and that's going to give us a better approximation over here. And we're going to use this expression to quantify the probability for getting particular outcomes. So this is going to depend on the value of x, and it's going to depend on the value of zeta. And we're going to analyze this expression in later videos as well. Another thing that we're going to do is we're going to follow a similar pattern when we construct the quantum algorithm for discrete logarithms. But the difference is we're going to have two control registers, and both of them will have alpha qubits. So we'll have two copies of this. And we're also going to have to apply an inverse quantum Fourier transform onto that other control register. And instead of the function f1 over here, we're going to have the function f2. But we're going to identify that the function f2 can be rewritten in terms of f1. And then we're going to use this relationship again. But we're going to have a different input to z. Instead, we're going to have z plus sh over here. And that's going to allow us to construct the quantum algorithm for discrete logarithms.